Morning all. Lecture 35, we only go up to 39. This is almost over. It's really scary. Okay. Announcements, you know that there's a project, you know that there's a fairly major checkpoint. We're trying to get you to do most of your work before the break. So this coming Tuesday, and then the final Tuesday is after the break. There will be homework assigned today. We're giving you the usual early submission deadline, and we implore you to get the thing done. It's not such a long homework. Get it done before you leave. But should you not get it done before you leave, then you can turn it in after the break. And some location changes in office hours, rooms. We talked about that last time. How many of you are in phase 2 of enrollment? A few? Any questions about courses? Anything? Yeah.
Oh, sorry. Will you be teaching Stat 28?
Am I teaching Stat 28? I am not teaching Stat 28. Elizabeth Purdom and Aditya Guntubuina are teaching Stat 28. They are following our course closely and are developing it. Stat 28 is multivariable methods. So as you can see, we did regression. We used 1x to estimate y. You could have used 17. We're doing classification. We're using a bunch of variables. So multivariable methods are the most commonly used, and they are going to do multivariable methods, and they are going to introduce people to R. Once you know one of these, learning the other is not that difficult. Learning both simultaneously for the first time is difficult, but you will go in with some pretty solid knowledge of the of relevant methods of Python, so that should be okay. I am teaching, of the new courses, I am teaching Prob 140, and that is filling up. I have 40-something students. I expect that is going to fill up. It satisfies all the stat requirements that are satisfied by 134, at least for stat. And for other departments, there may be some petitioning going on in the first semester, but I will be very surprised if there is any difference in requirements satisfying. There is a significant difference in the courses. The Prob 140 will... 134 only has calculus as a prereq, and so people come in from all over campus, and it has to be aimed at a very general audience, assuming no real common background. Prob 140, on the other hand, everyone comes from here, and everyone can therefore code, at least at the level at which we teach it here, and everyone, much more importantly, has a very solid practical sense of randomness. And so that means that course can really fly. And because you guys can code, you can solve problems that are just out of the league in 134 because they're trying to do everything on pencil and paper. I am enforcing that prereq. I have told a couple of graduate students who signed up for it that I will be kicking them out. And I don't know why. Apparently, anytime you put something for data science in a course title, suddenly everybody starts looking at it. Course questions? Anybody, anything before you have to sign up? All right. Okay. So what we'd like to do today is check that our classifier is actually worth using and see what we could do, with much simpler methods, because after all, we've had simpler methods for quite some time. And then I'd like to start talking a little bit more about categorical variables. All right, so finding the k nearest neighbors. Here's the program, which we executed, but I'll just remind you. Find the distance between your point. You have some fixed point whom we were calling Alice, and in the code we call new point. You find the distance between that point and every single point in the training set. So you have a bunch of distances. Usually we put it in an array. Then you have you go back to your training data table and you stick this column of distances on it. So each row is an individual in the training set. This new thing that you've tacked on is the distance between that individual and Alice. So there's one such distance for every individual in the training set. You sort them in increasing order, so your top k are the k smallest ones. And then you take the top k rows of that table, and that table gives you your k nearest neighbors. And I will just remind you that we did this. So let me run some data generation. So our data are 178 Italian wines. There's a dozen or so. Attributes, and the classes are ones and zeros, and we're trying to classify each wine. As we said before, today we're not going to cheat. Today we're going to develop our classifier on one set of these wines, and then we're going to test it on the remaining set. So what we're going to do is we're going to take this entire 178 row table, and we're going to shuffle it. So take a look at that first line. I'm applying dot sample to a table without a sample size. Therefore, by default, it chooses as many as we have rows. So it's going to sample 178 without replacement because of our option. And then we take half of them to be the training set and the other half to be the test set. And if you just look at those two data, so here's the training set. And here's the test set. They kind of look just like each other, and they're supposed to look just like each other. That is the point. You have split your two groups. You have split your original data set randomly into two groups. You are going to develop your classifier on one group. That's the one we call the training. And then we're going to test it on the remainder. In order to test it, what do we have to do? We have to take every single wine in this test set. So number one here, put it through our classifier and get a classification. That classification is going to be either a 1 or a 0. If it's a 1, we're happy because that's the actual class of this wine. If it's a 0, we're unhappy. All clear? And to measure accuracy, we're going to figure out what % of the time we're happy. Sound like a plan? Okay. So why did I take row 21? I want to take one of these ones. You know what? Why don't we just start with row 0? Okay. So I'm just going to look at this first wine in the test set, and that looks like that. You remember row objects are these weird things that have the elements annotated by column label. So this thing is in class 1. I am going to need to find its distances from everything else. So what I need is all its attributes. So we drop the class, and then we take people laugh at us for having very long variable names. But we have very long variable names so that when you go back and look at what we have done, it isn't called TWA, which means something else. You can just read the thing. So when you do your code, it's fine for you to use very cryptic variable names, just as long as you remember what on earth you're doing. And when you get somebody else to read your code, please expand those out and turn them into English. Okay. So now, we need to find the distance between this guy and every single one of these training wines. So we have a bunch of functions, and I am going to, okay, it just fits on my screen. Yes, okay. So all of this is code that you have seen before. I'm going to shut up. Read it. And every time you read something, or if you think you've already read it, shut your eyes, point, and then ask yourself, what type of thing is that? That is a reality check. So once you've had a chance to look at it, we'll talk through it. Anything looks murky, the first person to ask is the person next to you. Okay, so the distance between 2 points, we had the coordinates in 2 arrays, and that was what is known as the Euclidean distance. You look at the differences between the coordinates, square them, add them up, and take the square root. As basically an extension of Pythagoras' theorem to any number of dimensions. So what this does is if you give it 2 points, any 2 points, it finds the distance between them. Our job is to find all of the distances between our new point, our test point, and the entire training set. Yes? So we are going to first drop the class from the training set because we just need the attributes. And then we're going to define a function that says take this new point and find its distance from any arbitrary row. And then we apply that function to the entire table, so that gives you back an array consisting of the distances between your fixed new point named Alice and every single row of your training table. That is a very handy thing. And now you've essentially got what you need. You've got all your distances. So the next function, what does that do? You have your training table. What does the next thing do? Hello? It adds those points as a column, right? And the good thing about that is now you have the distances associated with all of the points, and therefore you can sort. And so finally, the last thing returns a table of the k closest neighbors, and it's a great idea to see what, we'll just go, and now we've seen this enough times that we'll go from top to bottom. So look at what it takes. It takes the training set. It takes the coordinates of your new point. And we are allowing any k nearest neighbors. So it takes how many nearest neighbors you want. It creates this table with distances, then it sorts the table by distance, and by default that's in increasing order, and then it takes the top k and it returns that. Top k is a what? It's a table, because it is some table and you've got a dot take, and that returns a table. Okay? All right, so let's actually do this. So I'll remind you that our test wine attributes look like that, and we are going to do, actually, let me not give it names yet. Okay, so I'm going to apply the function closest to our training set, to our test wine, and we're going to use 5 nearest neighbors. Ready? And that's what you get. So what are these? The test wine is this one. And these are the wines in the training set that are the closest. These are the distances between this wine and the 5 closest wines on the training set. And once you've done that work, your eye should go where? Just to the class column. These are our predictions. These are the nearest neighbors, right? So our prediction then is going to be, okay, I need to take this and find the majority, right? My eye can clearly see it's 1, and so now let me start giving this some names. Okay, and so from this, if I select class, then I get a table that looks like that. I can forget everything else. And what I want is a function that finds me the majority of, finds me whichever one as the majority. There are 300 ways to write that function. Here's one. Take a look. So it's going to take that table as its input. Takes a table, it figures out which rows you see ones in and counts that, then it counts the zeros, and then it returns the one that is the majority. And so if my table is called top 5 here, if I apply majority to top 5, what should I get? Should I get a table? What should I get? I should get a number. What should I get? I should get 1. I really should get 1. I get 1. Right? That's a good thing. And so now finally we can put this all together and we have our classifier. So I will again give you a few moments to read that. Note that the function classify is going to take 3 arguments. The first one is your training set. You should be imagining that as a table, your training data set. Then it is going to take your new point. I would like you to imagine that as a row of attributes of your new point. And then k is however many nearest neighbors you want it to have. Please, please, please don't be weird. Think of k as an odd number. Okay, so what's the first thing the function does? That line, if you wanted to put, actually, why don't we try putting a comment there? What is that doing? Find the k nearest neighbors and hello? Select their class column and then do what? Yeah, I just want to be a little clear when I say return the majority. Return the class that's the majority. So in other words, it's not returning you the number of majority votes, it's returning you a 1 or a 0 depending on which one was more frequent. Okay, so shall we run this? Yes? This should do everything at once. We've got the same test wine. What should the answer be when I run that? It should be 1, okay. All right, so far so good. So now what? Well, it would be good to have a reality check. Which wine was this? It was test set row 0. It was this guy. Our classification was a 1. What's the actual class? It's 1. So this one was fine. Now, obviously, you'd like to do it for every single one. Yes? All right. So we now need to put this classify function together. I don't think we need to run it again. Okay. So if I look at my test set, each one of these actually has a class, and then each one of these will have a predicted class. Yes? So we're going to have to count which ones match. You agree? So in other words, we're going to have 2 arrays, and we have to count how many indices give us equal values. So that is just a general array thing. You can write that in a 300 ways as well. Because we have arrays of numbers, I decided to say, okay, because we have 2 numerical arrays, if you're trying to see where they're equal, just subtract them and count the zeros. Yes? It's one way to go. We already have a function that is count non-zero. So that is an easy transformation to count 0. You agree? Yep. Length of array minus the number non-zero gives you the number 0. And then now if you have 2 arrays, numerical, that you want to count how many are equal, you subtract them and you count the number 0 in that difference. So what I'm asking you to do is to read this line and this line. Each of these is a 1-line definition. So count 0 returns what? Yes?
Are those 2 different ways to get the same thing, or do you need both to count how many were correct?
Okay, so in order to count how many were correct, I'm going to take my array of predicted classes and actual classes. I'm going to subtract them and count how many are zeros. All right? So this is something that takes, the first one is a function that takes a single array and just gives you back how many are zeros. The second function takes my 2 arrays, calculates the difference, and then tells me how many zeros there are in that. All right, so here is a function that evaluates the accuracy, and now you are experienced programmers now, so I'm going to do this over and over and over again. Everybody's phones come out and they take a picture of the screen. Okay, it's in the book. I'm going to do this over and over. Talk to your friend, read the screen, and see what's going on in evaluate accuracy. What are its arguments? The first one is your training data table. Yes? That second one, what is it? It's your entire test data table, right? Thus far, we've been feeding it one wine from the test set, but now we want to do the thing for every single wine in the test set. So we'll feed it the entire test set. Yes? And then K is the number of nearest neighbors, and now you read. Okay, what happened here? First line. We need the attributes, right? Because our classify function takes attributes of the testing individual. So we drop the class. We've got our testing individual, and now what are we doing here? We are classifying what? Who? Any single individual. You can call them Alice if you wish. Yep. And so every single individual gets classified, and any single individual can be classified by this function, and this function will return what? Return classify of something. Classify returns what? A 1 or a 0. Right? So for each single individual in your test set, you get back your classification. And now, because you want to do that for every row of your test set, you use our handy-dandy apply. Yes, when you apply a function to a table without the column index, what does it do? It feeds in the entire row, right? So it's going to be fed in the entire row of attributes. And it's going to find a distance, and then it's going to do that for every row. And so now, what is C? Type. Aha. Aha. C is obtained from what? What is test attributes? What is it? It's a table. We're doing a dot apply of something. Dot apply returns what? It returns an array. Yes? This thing is an array. So now we're going to count equal, because we wrote that function, our classification, which is C, and the actual class, which is in the column called class that we dropped before. Yes? And we're going to divide by the total number of wines in the test set. Okay. Questions about any of the lines? So I'm not expecting you to be able to go back and write this from memory, but I would like you to be able to read this and figure out line by line what's going on, so that when you write your own classifier, you can have it open in front of you and understand what happened in each line. And then you can put it together, because you can change the distance. We'll change a classifier in just a moment. All right. Okay, so we are ready to evaluate the accuracy of our wine classifier. I will evaluate accuracy by feeding in the training set, the test set, Y3, let's do 5. We're doing 5, right? Ready? Okay, at the end of this, what will I get? I will get a number, which is it's a fraction of some kind, right? It's a decimal, some decimal number, and I'm hoping for what? Nice high numbers, otherwise we've wasted a lot of time. So we're ready for this? Okay, about 90% accuracy. That's what you've got. While you're about it, same training set, test set. Shall we compare with 3 nearest neighbors? Yeah, we got a function. This is what computers do. So exactly the same data. Now we're going to look at 3 nearest neighbors and not 5. Close. So the first thing you can see is the number of neighbors does make a difference. While we're about it, 11 nearest neighbors, why not? Hovering around the low 90s, high 80s, low 90s. But so this is the same training and test set with different numbers of neighbors. Let me just change the set. Okay, so we are going to shuffle again, get a different training and test set, and evaluate the accuracy. 11 is a bit absurd. Let's try 3. High 80s. High 80s, low 90s. It's okay. It's okay. It's a pretty straightforward classifier. It's okay. What I would like to do is, now that we have a classifier, I'd like to use it on a data set that's a little more serious than classifying Italian wines. And for this, we are indebted to somebody who was 17 in 2012. Brittany Wenger won the Google Science competition by taking tissue that was from people who are being tested for breast cancer, running a classification algorithm. Actually, she had a neural nets algorithm, running an algorithm and classifying with high degree of accuracy whether it was cancerous or not. And so these are part of her data. Okay. So there's some tissue that has been extracted from each of these people, and there are various measurements on this. And in the end, there's a class, and 0 means not cancerous, and 1 means cancerous. Okay. And the idea was, can you use this? So this, and the point is that the tissue was extracted by what is called fine needle aspiration. So you stick a needle in and extract something. That is not an invasive procedure. It did not involve radiation. It did not involve any of this. So if you can do that and get an accurate classifier, that might be really, really helpful. So what we're going to do is we're going to try our classifier on this. Ours is not the same as hers, but we're going to try ours. So we are going to first create so we have 683 patients total. I'll take 341 in one group and 342 in the other. Does that sound like a plan? Yes? So the first thing we'll do is we'll shuffle all of the patients, and we'll pick the one half for the training set and the other half for the test set. Yep? Okay. So exact same code, different numbers of rows. And just to make sure that we have the right number of rows, so our test set has 342, our training set has 341. We're in good shape. Yes? So now, to figure out whether our classifier is any good, what do we have to do? What code do we have to run? Evaluate accuracy. That's a one-liner that we have to run. Evaluate accuracy of what are we going to feed it? The training set, the test set, and whatever K we want to use. And we've been using 5. We're on a 5 roll today. We're just going to use 5. Yes? Given that we have written all the code, that is all that you need to do to run your classifier and figure out the accuracy. Okay, here we go. This is going to take a while because there are now many more rows than in our wine table. There are 350 in each group. Not bad. Simple little classifier, 97% accuracy. She achieved something like 99.1. And one of the things she did was she had 3 kinds of points. Actually 2 kinds of points. The ones that she knew she could classify, and the ones where in her process it was not clear what the classification should be. So she had a separate category for those, and if you just looked at the ones that she could classify, she was very highly accurate, right? But you can see we're at 97, she's at 99.1 after having done quite a lot of work. This method isn't bad at all. There's a more extended discussion of this in your textbook. What I would like to do is actually pause and take questions and then see if, if we use some different kind of classifier, can we do as well? I mean, what's the value of the work is something that we should answer. So I'll take questions on anything we've done thus far. That's a very interesting question, and I don't believe there's a clear answer. The question was, where do you make the cutoff between how much training data you use and how much testing? We're doing halves. A lot of people use quite a lot for testing, quite training, and a little bit for testing. What happens with the test data is that the test data, there isn't a clear answer. We're just going to do halves. Is that there's not a clear impact, there's not a linear impact, that the more K you take, the more accurate you're going to get. After all, if you take K to be as many points as you have, everybody's going to get the same classification, right? So which K you should use, actually, now that you are very experienced data scientists, can you suggest a way to decide, say, between K equals 3 versus K equals 5? What would you do? Yeah, so you would create a training and test set by sampling at random, run both your classifiers, yes, test both. So one of them may give you, well, actually, here, we got 97 for our 5 nearest neighbor classifier. Here's 3 nearest neighbor classifier. We are about to get something someday. Not so bad. And you know that if I change the training and test set, both those numbers would change. Yes? So, and if we did it again, they would change again. So what will you do? Okay, so you can say, assume that you have the code. You either by a for loop or by using apply or something, you can figure out, you can repeat this process over and over again, and then what are you going to do? Make 2 histograms, exactly. Yes, this is what we've been doing all along, right? Run the thing over and over again, look at roughly the success rate for the 5 nearest neighbors and the rough success rate for the 3 nearest neighbors and pick. Yep. Now, maybe Henry put that on the project. I shouldn't do a project for you, but you know now that you can just run processes again. Yes? No, because I don't have a clear metric, right? See, I can minimize the distance because I know exactly what I'm minimizing, right? But here now, I don't know exactly what I'm minimizing. Yes? So maybe you want to maximize the percent, but it's a random percent, right? So we want to be a little bit careful here. This how many nearest neighbors you should take is a bit like I'm trying to predict y based on a bunch of x's. How many x's should I take? There's a serious aspect of art to that. It's not just, something that you can feed into a machine and pop out. There's much more than just airy-fairy, but in the end, there is some judgment calls to be made. Yeah. I'm sorry, which function? Yes. np.count non-zero, c equal to the column. Oh, absolutely. Absolutely. You can, as I said, you can write that function in 300 different ways. There's no reason to write that way at all. Especially, you should also take a look at the majority function. It's written based on a table for historical reasons. I think we wrote it like that last fall. But you can really do it on arrays. Okay, so what I want to do now is I want to pretend that we don't know any of this and that we don't want to deal with multiple variables. I just want to see what one attribute can tell us, because you remember that with the wine data, we plotted some attributes, and we saw that there was some separation. With these data, take a look at the data. You can see that these are numerical. However, look at the numbers. They're 1 through 10, yes? Each of those is a rating on a scale of 1 through 10. 1 being the most closest to uniform or the most closest to being a good kind of cell, a good kind of tissue, and 10 being bad, right? And so really these are categorical variables. And what I would love to see is if you just throw away all this machine learning stuff, if we just explore this, then what can we learn from even just one category, one attribute? So what I'm going to do is I am just going to look at this variable, uniformity of cell size. So I have in my training data set, and by the way, when we explore on the training data set. We do our worst on the training data set. We set our test data set aside. We don't mess with it until we have some kind of classification, right? Okay, so my training data set, what I've done is I've just gotten rid of all of the data except uniformity. I have no idea what this looks like, but what I would like to do is see, is the uniformity different in the two classes? Does that not seem like a reasonable question? Yep. Okay, so that's your table. You've been X number of weeks in data 8. What are you going to do to the table to figure out the distribution of uniformity in class 0 and in class 1? Okay, so talk to your neighbor, go back through your class. You know how to do this. You know how to do this. So you have something that's classified, there's a categorical variable, and there are two classes, and you want the distribution in each of the two classes. There is something. So what do you have to do? For class 0, you have to figure out how many uniformities were 1, and then you have to figure out how many were 2, and how many were up to 10. And then you have to do the same thing for class 1. And you have a technique. You really, really do. You really, really do. It is a method. Pivot. Yes, that is what pivot does. It cross-classifies data by two variables. This is why we taught you pivot, and we've been trying to bring it back over and over again, because you can't do any of this stuff without pivot. Here we go. This one, training data cell size, we are going to pivot by class and uniformity. And we are going to get exactly what we want. For class 0, these are the counts at every level of uniformity. For class 1, these are the corresponding counts at every level of uniformity. Yep. So now what? One is cancerous. Yeah. All right? So pivot does what? You take your table, when you pivot, it cross-classifies your data according to these two. So the class is either 0 or 1, and uniformity is some number between 1 and 10. When you put class first, how does that affect your output? Those are the columns, and everything else are the rows. All right. So I've got these. I'd like to compare. If I just look at those numbers, those two distributions don't look the same to me. Yes, they really don't look the same to me. However, these are counts, and the counts are not the same in the two columns. So, for example, there are 231 of these and 341 total, so it's not half and half. So the counts are a pain to compare. Therefore, what should I do? Proportions. Okay, we are going to define a proportions function. that takes an array and divides by the sum of the array. Yes, we are going to create the corresponding proportions table. We've done this before when we did total variation distances and so on. Yes? And we are going to draw the bar graph of the proportions, and now look. The blue bars are not cancerous. The gold bars are cancerous, right? So what have I done? I have thrown away all of the data except this one variable, and I'm looking at this, and just this one variable, we should be able to classify based on this. You agree? The two look quite different. So I'm going to try a really dumb classifier, right? The really dumb classifier is I am going to take this new test set tissue. I'm going to compute its uniformity. If that uniformity is bigger than 3, so if it's 4 to 10, yes, I'm going to say gold, otherwise I'm going to say blue. Right? It's worth a shot? So what's my classifier now? What do I have to do to my test set? I have to go to each value, right, each row, forget everything, just look at the uniformity column, and what am I looking for? Is that number bigger than 3 or not? Yep. If it's bigger than 3, I'm going to say 1. If it's anything else, I'm going to say 0. Yep. Well, I don't need to write any nearest neighbor classifier or anything. I can just count. So I'm just going to show you what happens if I just take the first 4 of my test set. Yes? What I have to do is I have to find the column that's uniformity, and I have to compare to 3. And so if I run this, I get an array of 4 trues and falses. In my test set, the first one was not bigger than 3, the second one was, the third one wasn't, and the fourth one was. Yep. So if I run my entire test set of 342, then I'm going to get 342 of these guys, trues and falses. Yep. And then what do? What do? I've got 341 trues and falses based on this silly classifier, and I've got the actual 341 trues and falses. Yes? I compare. Good? All right. So classification is going to be, I'm going to take the whole lot of uniformities. I'm going to compare to 3. I'm going to get a whole lot of trues and falses, which are the same as 1s and 0s. You know that. Yep. And so I'm just going to count equal the classification column and the test set column, which contains the actual 1s and 0s. And if we do that, we get 93%. By doing something really, really crude. Forget all of the data, keep 1, and just stare at it and do the simplest possible thing. Already your accuracy is very high. Yep. So was all the previous work not worth it? It most certainly was. If you are going to get tested for cancer, right, you want as much accuracy in your tests as you can. The point I'm trying to make is that the basic methods are also good. Right? And before we had all this machine learning stuff, people were tested for cancer, and answers did come back, and it was things like this that made the difference. And so this is a good method to use. And it allows us to extend to answer some questions that we haven't thus far been able to answer, which is we have categorical variables now. Remember with our with numerical variables, we have a measure of x being related to y. If you want to see if x is related to y, what do? You first draw a scatter diagram. Yes, numerical variables. You have a measure of linear association. You have a number. But when the two variables are categorical, like class, cancer, non-cancer, and uniformity, very uniform, a little bit uniform, etc., not uniform at all, then how do you measure the relation between the two? That's quite a serious question, and we don't have a measure for it yet. Yep? And so we can explore in exactly the same way. And I'm going to look at the variable mitoses. They count the amount of mitotic activity in the cell. And please note what I have done. I have relabeled the class cancer and not cancer. Yes? Just because people keep asking me which one's the 1 and which one's the 0, and this way we don't have to ask that. Okay. And what I'd like to do is take a look at the distribution in the two groups. So what we did here is exactly what we did for uniformity. We're doing it on the entire data set, right? Take a look at those two distributions. Do they look the same or do they look different? There's this issue, right? You have a small number in a long tail in the blue distribution, and the bulk of them seem to be low in both cases. Yep. So what question does this arise in your head? You're data scientists. For 12 weeks, I have been teaching you to turn into Eeyore. You have to be the most pessimistic person in any room. These two maybe look different, but what does the data scientist always say to rain on people's parades? It could be due to chance. It could be due to chance. Yes? So why is chance? Well, this data set is a sample from a larger population. Remember those new people that come in that we want to test and classify? There's a larger population, and maybe in the population, none of this makes a difference. But in the sample, it looks like it. Okay, so today I'm just going to show you some pictures, and then on Monday we're going to do the details. All right, so if it was nothing going on, then do you remember doing something like this before? We have two groups. We're trying to test whether a variable is related to the groups at all. In a very, very different context, we did exactly this. Footballs, Deflategate. There were the Patriots balls and the Colts balls. And they had various numbers, and the questions were the numbers similar? Yep, what did we do? We shuffled all the numbers. Yep, so I'm just going to show you what happens when you shuffle. So if nothing's going on, I could shuffle all these mitosis values, right? And the distribution should be about the same. So I'm going to shuffle. And there are the classes of the people, there are the actual mitosis values, and these are the shuffled mitosis values. Yep. And now what we're going to do is we're going to take a look, we're going to compare the two shuffled distributions. The two shuffled distributions look like this. Right? For the shuffled data, the two distributions look like this. For our original data, the two distributions look like this. Yes? What do you think? Looks like a random sample? Doesn't look like a random sample. What do you think? Well, you got to do, it looks like something else. Your gut is saying it looks like something else. Yep. How do you figure out whether it looks like something else? You have a null hypothesis, ain't nothing going on. You have an alternative hypothesis, something going on. If the null were true, you should look something like this, but it looks like this. Yes? How do you actually formalize that? You come up with a what? P-value is the last thing. Before that, you come up with a test statistic. Yes? You're trying to say two distributions look the same. What's the test statistic? Total variation distance. Yes? And so you will find the total variation distance of the shuffled data, and then you will compare it to the one that you actually got, and lo and behold, you have a decision. Yep? Okay, so I'm going to let you go this weekend.